What's up, guys? It's me, Sir Ernest, and today we will discuss a sample problem related to Hamiltonian dynamics. The problem reads: a particle is free to slide along a smooth cycloidal trough or through whose surface is given by the parametric equations x equals a over 4 times 2 theta plus sine 2 theta and y equals a over 4 times 1 minus cosine 2 theta, whose theta ranges from values from 0 to pi and a is a constant. So you will notice that this is actually problem 10.11 of Fowles 7th edition, and originally this is your problem set. But in this case, we're going to modify this problem wherein instead of using the Euler-Lagrange equations, we're going to find the equation of motion of the particle using Hamilton's canonical equations. Okay? So from your problem sets, we know that the Lagrangian, but again, this is from your problem set. So the Lagrangian is given by m a squared theta dot squared over 2 times cosine squared theta minus mga over 2 times sine squared theta. So you will notice here that the system has only one degree of freedom, and that is theta. And that's because the Lagrangian is only an explicit function of theta and theta dot. Okay? So from here, we can actually calculate our generalized momenta, p theta, and from here, we can calculate or determine the Hamiltonian of the system, which should be a function of theta and p theta. Okay? So from the Lagrangian of the system, we can calculate the generalized momenta. The generalized momenta is p theta, and that is equal to the partial derivative of the Lagrangian with respect to theta. So from here, theta dot. Okay? Yeah. So that means we only differentiate this part of the problem. Okay? So now we have m a squared theta dot cosine squared theta. Okay? So from here, we can substitute this. We can substitute theta dot in terms of p theta. So this is p theta divided by m a squared cosine squared theta. So that means our Lagrangian can now be rewritten as, so this m a squared cosine squared theta over 2 times theta dot squared. So this is p theta over m a squared cosine squared theta squared minus mga over 2 sine squared theta, or L is now equal to p theta squared over 2 ma squared cosine squared theta minus mga over 2 sine squared theta. So here we we were able to express the Lagrangian in terms of theta and p theta, which we need to use to calculate or determine the Hamiltonian of the system. So, from here, we can calculate the Hamiltonian of the system as follows. Okay, so Hamiltonian, because we only have 1 degree of freedom, so therefore the Hamiltonian will now be equal to p theta theta dot minus the Lagrangian, which is equal to p theta times theta dot, which is this one. So this is times p theta over m a squared cosine squared theta minus the Lagrangian. This is p theta squared over 2 m a squared cosine squared theta plus, this is minus Lagrangian, so minus minus, so that's plus mga over 2 sine theta. Okay, so from here we can express the Hamiltonian as follows: p theta squared over 2 ma squared cosine squared theta plus mga over 2 sine, sorry, this should be sine squared theta, sine squared theta. So our Hamiltonian is now a function of theta and p theta. Okay, so now let's compute for the equation of motion. So the equation of motion will now be expressed or rewritten as follows. So equation of motion, so partial derivative of h with respect to p theta is equal to theta dot. So this is now equal to this one. So this is p theta over ma squared cosine squared theta. Okay, which follows that p theta is ma squared theta dot cosine squared theta, which is what we calculated earlier here. Here, this one. So that's m a squared theta dot cosine squared. Okay, so in other words, this equation verifies the generalized momentum that we calculated earlier. So that means if you have an Hamiltonian and then you calculated the first equation of motion and you got a different answer from the first try, you calculated the generalized momentum through the Hamiltonian, therefore something's wrong. Okay, so from here we can now get the next equation of motion, which is negative p theta dot equals partial derivative of h respect to q at theta. Okay, so this is your Hamiltonian. So this is a function of theta, this is also a function of theta, so therefore you can now calculate this as p theta squared over 2 ma minus partial derivative respect to theta of cosine to the negative 2 theta plus mga over 2 times the partial derivative with respect to theta of sine squared theta. Okay, so this is equal to negative total derivative with respect to time of ma squared theta dot cosine squared theta, and this is equal to this plus this. So simplifying this or evaluating the derivative, we now have p theta squared sine theta over ma squared cosine cube theta plus mga sine theta cosine theta. Okay, this one is now equal to, because theta dot and theta are both functions of time, so we use product rule and then chain rule. Okay, so this is ma squared, that's a constant, so this is negative ma squared, so times copy the first, so this is theta dot times derivative of cosine squared theta with respect to time, so this is now 2 cosine theta times derivative of cosine theta, which is negative sine theta. Okay, so plus cosine squared theta times derivative of theta dot with respect to time, so that's theta double dot. So that's theta double dot times cosine squared theta. And then this is equal to sine theta over ma squared cosine cube theta times p theta squared, which is m a squared theta dot cosine squared theta, then squared, and then plus mga sine theta cosine theta. Okay, so now let's you can now simplify this. Of course, we can cancel m and then, so remember, this is, if we're going to distribute this, we now have square m squared a to the fourth theta dot squared cosine to the fourth, so m will cancel here, one of the m's will cancel here, and then this m will be cancelled, and then one of the a's here will cancel, so this a to the fourth will cancel with this, so this is squared, and then we can cancel it here with this one, and then of course there is cosine here, there is cosine here, this is cosine cube, will cancel with to the fourth here, and then cosine will cancel here, will cancel with this one, and then this one. Okay, so let's clean this up. We now have your equation of motion, which is negative, negative, that's positive. Sorry, this should be, sorry about that. Okay. Okay, so this is 2a theta dot sine theta, so 2a theta dot plus minus plus sine theta plus a theta double dot cosine theta equals, so this is a theta dot squared sorry, this should be, sorry about that. So this should be squared. Y, so that's 2, so take theta dot times 2 cosine theta, its derivative of cosine theta would be negative sine theta, then derivative of theta, which is theta dot, so that's squared. Okay, so this is squared. Okay, let's go back here. So this is a theta dot squared sine theta. Okay, then plus mg, sorry, g should be g. Okay, sorry about that. So this is yeah, so this is g sine theta. Okay, so we know that we can combine these two. So this becomes a theta dot squared sine theta minus g sine theta minus a theta dot cosine theta equals 0. So this is now your equation of motion. Okay, so this is theta dot. Okay, so this is what we actually got when we use the Euler-Lagrange equation. Okay, now let's look at this equation a little bit deeper. Okay, so again, this is what we got using Euler-Lagrange equation. Now let's look at this equation a little bit deeper. Now let's say if we're going to, let's say, parameterize this, or suppose that we define variable s be equal to a sine theta. Okay, from here we could get that s dot would be equal to a theta dot cosine theta, and then s double dot will be equal to a theta double dot cosine theta minus theta dot squared sine theta. And what is this? S double dot a equals theta equals a theta double dot. So where this here this should be theta double dot. Sorry about that. Yeah. So this one and this one would be s double dot, and then that's g over a sine theta. So this is plus g over a s equals 0. And what do you notice here? This is actually a simple harmonic oscillator or simple harmonic motion. Okay, so under this parameter, our particle will actually move in a simple harmonic motion. Okay, amazing. I hope this is clear. Well, thank you for watching. I hope you learned something today, and I will see you guys in the next video. Bye bye.